All right, today we're going to talk about the heap data structure, which is not the heap memory. The heap data structure is one of these structures that does a very specific thing, but does it very, very well. And it does pop up here and there. It's not so much a general structure that people use all the time, but what happens is a lot of times you're doing, I don't know, certain algorithms or certain procedures, and all of a sudden the heap just fits like a glove. And so we're going to talk about the heap, which, by the way, is a type of binary tree. It's not a binary search tree. It's a binary tree with what's called heap property. And the one nice thing about this heap property is you can use it to do a heap sort, which is another n-log-n sorting algorithm. All right. Why do we study a heap sort? That's good. It's well-known traditional sorting. Okay, that's nice. Quick sort, that's great. Quick sort's generally faster than heap sort, but heap sort is better for critical time applications. The other nice thing about heap sort is that it's in place, unlike merge sort, so you get guaranteed n-log-n, and you don't have to allocate more memory. So what's a heap? Okay, here's where the sadness begins. Definitions of a heap. Memory, the large area of memory from which a programmer can allocate blocks as needed and deallocate them, or allow them to be garbage collected when we no longer need it. This is what you've been thinking of a heap so far. The data structure is a balanced left justified binary tree in which no node has a greater value than its parent. All right, what's the similarities?
It's a bunch of stuff.
All right, they both have stuff in it.
But like a bunch of it, not like a stack with a little bit. It's
Okay.
A bunch of stuff.
Well, you could have the heap data structure not have many items, and the heap memory could not have many items. They have very little in common. So now, unfortunately, this is why it's sadness. When we say the heap, we have to keep in mind in context if we're talking about the memory or the data structure. Unlike the stack, in which case they're effectively they're basically the same thing. Heap sort, or a heap, uses the data structure, of course. All right. What is a balanced binary tree? Well, recall the depth of a node is the distance from the root. The depth of the tree is the depth of the deepest node. Binary tree of depth n is balanced if all of its nodes at depth 0 through n-2 have 2 children. AKA, you filled out every single level or row except the last one. So that's balanced. That's perfectly balanced. This is also balanced because this row is full, this level right here is full, this level is full, this last one is not full, but it's the last one. So that's okay. So it's still balanced. By the way, this is important to keep in mind what balanced means because it's part of Project 3, which I forgot we should have talked about first, but that's okay. This is not balanced. Why is it not balanced?
n-1 has something missing.
Yeah, there's one over here. So you took this node and you moved it up here, then it would be balanced again. Why do you think we want it balanced?
So it won't degrade performance.
Right, doesn't degrade performance, and if it's balanced, you're basically guaranteed log-based performance for all of your operations. So keeping things balanced is very desirable and advantageous. All right, left justified. So that was balanced. The other term of a heap is that it needs to be left justified. So first term is it has to be balanced, like we talked about, and then we have to also make it left justified. So this is left justified. Okay, we're not going to say what it is. Okay. All leaves are at the same depth, and all the leaves at depth n+1 are to the left of all the nodes at depth n. Okay, what does that mean? Basically, the easiest way to think about this is you're filling up the rows from left to right. So here, then here, then here, there, there, all the way to the beginning, and you're filling it up here, and then you stop once there's no more nodes to add. This is not left justified because on this final row, there should be a node here. So we took all these nodes and shifted them all to the left effectively to where the 2 open spots were over here on this side, then it would be left justified. All right. Ooh, a plan of attack. First, we'll learn how to turn a binary tree into a heap. Yeah, whatever. Next, we'll learn how to turn a binary tree back into a heap. Okay. We will see how these ideas sort an array. Cool. The heap property. All right. So the heap has to be balanced, and we talk about why that's advantageous. It has to be left justified. We haven't talked about why that's necessary, but that'll make more sense in a bit. But the third property is that it has to have the heap property. And a node has a heap property if the value of its node is as large or larger than the value of its children. How is that different than the binary search tree?
The binary search tree just had something in the middle.
Something in the middle, right. So everything to the left was less than, everything to the right is greater than. In here, your children, well, in this case, you are larger or greater than your children, is what it means. So this has the heap property because 12 is greater than both 8 and 3. This has a heap property because it's 12 is greater than or equal, we do say equal to 8 and greater than or equal to 12. This does not have the heap property. How can we make the tree on the right have the heap property?
So we swap 14 and 12.
Yeah, so we can just swap 12 and 14. Perfect. All leaf nodes automatically have the heap property since they have no children. That's beautiful. A binary tree is a heap if all the nodes in it have the heap property and it's balanced and left justified. All right, sift up. All right, we're going to talk about this. Given a node that does not have the heap property, you can give it the heap property by exchanging with a larger value. Do it. Good morning. All right, come on.
15 minutes late. No story for you.
Yeah.
Story?
No story.
No. Oh, what did I say? I thought it was 15. What did I say?
I thought it was 20.
Oh, it's 15 now. What's your story?
Well, there was a lot of traffic on I-27.
No. Don't give me. Okay, fine.
I'm not done yet.
Okay.
Because the Lizard and Doc Ock were there for some reason.
Oh, wow.
Like, normally they're in New York, but they were down here for some reason. And so it took Spider-Man a while to come down so he could defeat them.
Did you help Spider-Man out?
Unfortunately not, because there were like 8 cars in between us, but... And also my costume's at home, so...
Oh, wait a minute.
I hope more people come in now.
I was going to ask if you took any pictures, but I guess not.
Can't like text and drive or take pictures and drive.
That's illegal.
It is? No. So the blue node does not have the heap property. We can fix it. Oh, look at that beautiful arrow. Swapping it to the heap property. Yeah. So the top node has heap property. Heap property being that you're larger than your children. This is called sifting up. Notice that the children may have lost the heap property when this happens. Constructing a heap, part 1. A tree consisting of a single node is automatically a heap. Well, does that make sense? If it's one node, it's balanced, it's left justified, and it has the heap property because it has no children. All right, great, perfect. We construct a heap by adding nodes one at a time. Alrighty then. Add the node just to the right of the rightmost node at the deepest level. Why do we do that? Because that forces it to be left justified and balanced by putting it there. If the deepest level is full, of course, start a new level. And here's an example. So if we have something like this, we add a new node here. So you're always adding it from left to right, which guarantees it to be balanced and left justified. All right. And if you're on this side, you'd add the new node at the next level. How are we doing? All right. Well, only problem is there each time we add a node, we may destroy the heap property of its parent node. So then we have to sift up. Each time we sift up, the value of the topmost node is sift may increase and may destroy the heap property. I hope we get some examples. So we have to keep sifting up until we either reach a node whose values don't need to be swapped because the parent is still larger than the children, or we're at the root. because once we're at the root, we don't need to go up anymore. Give me an example. Okay, good. We have 8, we add 10. Oh, look at these nice transitions. We need to swap the 10, so then we get a 10 and an 8. Doing well, all right. We add a 5, do we need to do anything? Great. We add a 12, do we need to do anything?
Yeah.
So we first have to swap with the 8. Do we have to do anything again?
Yeah.
Yep, so now we gotta swap with the 10. Oh, good. Okay.
And then if if it was a smaller value than the 8, we have to swap them. I mean, it's not because we had switched originally. But if somehow that had worked out that then there was a smaller value down there.
Great question. Other children are not affected. So in this example, we add a 14. We swap with the 10. We don't need to check the 8. Why don't we need to check the 8? Because since the 14 is greater than the 10, and we already knew the 10 was greater than the 8, we don't need to check that. So because of the heap property, we only have to sift up. We don't have to actually start scanning down any branches. And then we sift again or swap again with the 14, and we're done. Now here's what's tricky. Now this is what you were probably asking. If you swapped here and made this number less than, could it affect the 8? No, because this number on top has to have been equal to or greater than the 10. So because of the heap property and the way it cascades up, we don't have to keep searching, which is great and one of the hugest advantages of a heap. The node 5 is not affected either because the parent gets larger, not smaller. Perfect. Node containing 8 is still not affected because though the parent got smaller, its parent is still greater than it was originally. All right, here we go. Sample heap. After it's been heapified. Oh, perfect. There, everyone got that? Heapified, technical term. Again, is this a binary search tree? No. What can you tell me about the 25?
It is the greatest number
It is the
on that tree.
greatest number. Is that always going to be the case of a heap?
It will always be tied for the greatest number.
It'll be the greatest or tied for the greatest, yes. So the root always is the greatest of everything, or equal to the greatest of the entire heap. Heapified does not mean sorted. Some people get that confused. Keep in mind the heap property is not the sorted property. It is just heaped. Heapifying does not change the shape of the binary tree. The binary tree is balanced and left justified because it started out that way. Removing, okay. All right, we remove the root. Hey, look, a stray arrow. So we discard the root. If we discard the root, we need to add a node to there. So the first step with the heap is you always want to make sure you maintain the balanced and left justified property. Balanced, it should be intuitive. Left justified, we're going to get to pretty quickly. But in order to satisfy that, if we remove the root, then we need to move effectively the last element of the final row up there. And by moving the 11 up there, the binary tree is now balanced and left justified. It may not be a heap anymore, but at least it's balanced and left justified. There it is. All right. Now what do we do? Well, beforehand we sifted up. Now we're going to
Don't we just need to?
first time we sifted up.
You may have to sit there.
Now we're going to sift down. So when you add something, you sift it up. When you delete something, you sift the new value down. But it's no longer a heap. Only the root lacks a heap property. Well, that's convenient. We sift up the root, or sift down is what I prefer. There we go. So we're going to, look at that. To sift down, you look at your two children and you find which one's the largest. Why does it need to be the largest? Because if you're going to swap, you need to make sure you're larger than all of your children. So you swap with the 22. Now, very important. Is this 22 in the correct location?
Yes.
Yes. Because the heap property's been maintained, that node is in the correct location already. We don't need to mess with anything else on that side of the heap. But we're on this side, so we need to, is this 11, I'm sorry, in the correct place? No, so we need to swap it with the
22.
22. Beautiful. Is that 22 in the correct location now?
Yeah.
Yep. So every time you sift down, you're putting it in the correct location. And every time you sift, you're basically cutting off half of the binary tree that you need to search. Hey, what does that mean this algorithm is in Big O?
Log n.
It's log of n. And it's guaranteed to be log of n because it's a balanced binary tree. All right, of course, we need to do this again. So we switch the 11 with the
21.
21. Perfect. We repeat this and so we can do this until the tree becomes empty. So we can keep removing. Notice the heap, you only remove the first element. That's why this heap is a little tricky. You don't remove any random element in a heap. You can, but it doesn't make any sense. The point is to remove the root element. Why would you want to only remove the root element?
You only want the biggest.
You only want the biggest. Why would that be handy? If you're always removing the root, you're always removing the largest or the next largest. What does that sound like?
Sorting.
Sorting! Yep, so you can remove it, sorting it. Every time you remove it's log of n, and you have to do it n times. Hey, it's n log n. All right. Okay. All right, so sorting. Actually, before we get to sorting, how do we store this data structure? Because I haven't talked about that, and there's a specific reason why. You who have taken this class before, don't say it.
All right, I'll be quiet then.
Do you want the smaller stuff on the left?
The smaller stuff on the left. How do we store this? Here's the trick. Let's see, does it tell you? Here's the neat part. All right, you ready?
It's the slice and now.
Because the binary tree is balanced and left justified, it can be represented as an array. In other words, the heap is an array. It's not a binary tree where you have a binary nodes pointing to your children. No, it's actually an array. So, and that's because it's balanced and left justified. Why does it need to be left justified if it's an array? Because if you want to add to the array, it's real easy. You just put it at the end of the array. There, it's now balanced and left justified. That's why it was going out like that. But the real question is, how do we represent this binary tree as an array? Well, operations on binary trees can be represented as operations on arrays. Perfect. To sort, heapify the array. Okay, that's great. We're going to get to that later. So how do we map this into an array? Because that's what's important. It looks like that, except the numbers are slightly off. Here, notice 25, 22, 17, 19, 22, 14, 15, 18, 14, 21, 3, 9, 11. I just read it from the top and moving left to right in each zone, and that's how it is stored sequentially inside of this array. So where's children of 25? It's 22 and 17. What's children of 22? It's 19 and 22. What's children of 17? That should be 14 and 15. Huh. Do you think there's a formula to figure out what this is?
Yeah.
Yes. Oh, the back of this chair broke. Okay, I'm not using that. So, let's see here. So the child of node n, is that hard to see?
For me, I have like that white stuff.
Oh, that made it worse. let's call it the left child of n. What would be the left child of n? Well, let's make it easy. Let's start it easy. It has to be at least n, right? Because it's going to the right. And the left child, well, if we're at root, you just went over 1, right? So it's something plus 1. All right, this board really needs to be clean. Hopefully this makes it better. Oh, that made it way better. Oh, that's better. Okay. But if we're at 1, it's not 2, it's actually 3. If we're at 2, it's not 3, it's actually the 5. Well, does anyone see it?
Is it the first number plus the second number?
Oh, that's an interesting guess. I like it. Yes, it is. That is correct. Huh. Well, so that means it's, yeah, that's correct. It's an interesting way, so it's n plus 1, right? Is what you were saying.
Yeah.
Also known as just 2 times n plus 1, right?
Yeah.
Yeah. Yeah. Didn't think of it that way, but yeah. All right, what about the right child?
It's
2n plus 2.
2n plus 2, yep. 2n plus 2. Oh, well that's not that hard. How about, and one other operation we need is the parent of n. Parent of 1 is 0, the parent of 2 is 0, the parent of 3 is 1, the parent of 4 is 1, the parent of 5 is, the parent of, hold on. The parent of 5 is 2, the parent of 6 is 2. Did I do that right? Yes. So we need 6 needs to go to 2, 5 needs to go to 2, but 4 needs to go to 1, and 3 needs to go to 1. Huh. Goes to 3, 8 goes to 3.
There's a lot in there somewhere.
Oh, is it just divided by 3?
Divided by 3?
No.
Not 3. 5 divided by 3 is not 2.
No.
But instead of dividing by 3, what happens if we divide by 2? Well, we're close. 6 divided by 2 is 3, but 5 divided by 2 is 2. 4 divided by 2 is 2, but 3 divided by 2 is 1. So we're getting half of them but divided by 2, so that's close. What do we need to do?
So subtract 1 by 3.
There we go. Yep. N minus 1 divided by 2. 6 minus 1 is 5, divided by 2 is 2. 5 minus 1 is 4, divided by 2 is 2. Or divided by 2 is 2, there we go. 4 minus 1 is 3, divided by 2 is 1. 3 minus 1 is 2, divided by 2 is 1. 7 minus 1 is 6, divided by 2 is 3. 8 minus 1 is 7, divided by 2 is also 3, because we're doing integer division. All right.
suddenly that weird mechanic that they teach you in procedural is useful.
This is not going to be the only time. A weird mechanic. All right. Notice the left child of index I is 2 times I plus 1. The right child is 2 times I plus 2. And therefore, yeah, the children of node 3 are 7 and 4. So given any element, or index, I should say, of the array, we can immediately determine both the children and the parent. In a way, that's cool because that means that each node now has pointers to its children and a pointer to its parent, although it's not really a pointer, it's just a way to calculate where those reside. But it would be similarly if we had a binary tree node with those pointers. Okay. All right, I think we need to start coding things. Yeah. All right.